Hello, everyone, and thank you for joining this webinar. My name is David Curry, and I am Senior Vice President of EDEM and CFD products at Altair. During today's session, we'll be outlining two key solutions available within the Altair ecosystem, which are designed to simulate how granular materials and fluids interact. That's EDEM AcuSolve and Barracuda by CPFD software, which is available on units through the Altair Partner Alliance. During the session today, we will explain each solution and their key features, how they complement each other and when to choose one or the other, and also how you can get started with using them. A few housekeeping notes before we begin. The presentation will last approximately 45 minutes, and afterwards we will have a Q&A session. All the lines are currently muted, but if you do have any questions, please feel free to use the chat box during the presentation, and questions will be addressed at the end of the session. This session is also being recorded and will be posted to the Altair Resource Library, so you can watch it again or share it with your colleagues later. So joining me in the presentation today are Peter Blazer, CPFD Operations Vice President, and Ravi Tega Chaganti, Senior Product Specialist, CFD at Altair. Welcome, Ravi and Peter. I'm delighted that you can present alongside me today. But to get started, let's set some context and talk about granular materials. And the first thing you need to know is that the world is full of them. Now, whether you think of them as granular materials or rocks, powder, tablets, granules, or perhaps even just good old-fashioned dirt, granular materials are everywhere. In fact, they're present in something like 70% of all industrial processes. For example, in mining, you have things like iron ore being mined or transported on conveyor belts. In the pharmaceutical sector, bulk materials and granular materials appear in the form of powders or tablets being processed. And in agriculture, grain being harvested or soil being plowed. And where you have these industrial processes, you invariably find that there's an engineer trying to make sense of what's going on. And getting a grasp of designing for granular materials can lead to significant improvements in the performance of a piece of equipment that needs to handle, transport, and operate in such environments. The challenge is, though, that these materials are complex in their behavior. So, for example, if you consider an excavator going through sand, if that sand is dry, then it will behave more like a fluid. It will be very free-flowing, and an excavator bucket will likely pass through it very easily. However, if you get that same sand material wet, it will start to become cohesive and sticky with very different properties that will significantly affect the loads acting on the bucket and the surrounding equipment parts. This inherent variability is seen across industries for many material types and numerous different types of applications, and where understanding the behavior and influence of granular materials is vital to a successful design. And if we take that a step further, in many cases, the granular material does not exist in isolation. Their behavior is significantly influenced by the liquids and gases in which they are found, and this further ramps up the design challenges that engineers face. The type of particle fluid behavior can vary greatly, either from dense phase to more dilute flows. There can be heat transfer, chemical reactions, or you can be talking about an application that's at a small scale, such as in the case of a vacuum cleaner, right up to the largest of chemical reactors. These particle fluid or multi-phase flows are encountered across industries, including the energy sector, agricultural applications, mining, oil and gas, chemicals, and pharmaceuticals. Now, sometimes the particle fluid behavior is simply coincidental to an application, but would still need to be captured as part of the design process. However, in other cases, the use of fluids is fundamental to the success of a particular process. So, for example, fluidization of materials to encourage drying or reactions, or the use of airflow to separate crops within agricultural applications like harvesting, means getting the right particle fluid interaction is critical to a design. In these multi-phase cases, the way particles of fluid interact adds another layer of complexity that an engineer must address as part of their design process. And such systems with the increased behavioral complexity have also become more increasingly difficult to evaluate using traditional design methods such as physical testing. And so simulation offers a great way to gain insight into what is happening in a particle fluid use case. And so today we want to help you understand the solutions you have available on Altair units and to help you understand when to use which solution for your application. And with that, I will hand over to Ravi Tega-Chiganti, our Senior Product Specialist at Altair, who will share more insight into our EDEM AcuSolve coupling before he hands over to Peter, who will discuss the Barracuda Virtual Reactor. Over to you, Ravi.
Thank you, Dave, for the great introduction to the fluid particle flows that we come across in various industries. So in the next few minutes, I'll talk about the various tools and softwares that are present or available in the Altair software ecosystem that can be used to model these granular flows as well as fluid flows, and how we can combine the best of these both tools to simulate particle fluid multiphase flows. So first, starting with EDEM. EDEM, as you know, is a very high performance software that can be used for modeling granular bulk material flows, and it is powered by Discrete Element Method. In short, we call it DEM. And EDEM can be used to simulate the behavior of bulk materials such as fine powders, coal, ores, and granular materials such as agricultural crops, grains, and other waste materials. And using EDEM, engineers can derive crucial insights into how bulk materials interact with equipment as well as the other materials, and how these tools can be used to improve the operational efficiency and overall drive the productivity and throughput of these systems. And AcuSolve, which is a general purpose CFD solver that is based on finite element method, comes with a broad set of features ranging from single and multi-phase flows, as well as heat transfer. And the capabilities of AcuSolve can be coupled with additional tools like OptiStruct, EDEM, and MotionSolve to simulate various multiphysics simulations. So next, we'll talk about how we can combine the capabilities of EDEM and AcuSolve, and also individual capabilities in these tools to simulate various ranges of granular flows, fluid phase flows, and coupled particle fluid flows. So far we have seen various examples of the granular general industrial flow process that happen. And in order to capture the fluid phase behavior as well as the particle phase behavior, we need to have the right tools to model the physical behavior accurately. And AcuSolve single phase fluid flow capabilities supports a wide range of use cases, varying from steady state flows, transient flows, and heat transfer. And it also supports a feature called AcuTrace that can be used to simulate the transport of fine particles then it can be used to simulate the dilute phase flows. And the multiphase capabilities in AcuSolve can be used to simulate even dispersed flows by taking into account the interaction of the fluid phase on the particles. And the Eulerian granular multiphase flow model that is available in AcuSolve can be used to simulate the high solid concentrations up to 0.63 volume fraction of solids, where the effect of both the fluid phases is taken into account on each other, and the solid phase effects are modeled through the kinetic theory of granular flows. So, and these models available in AcuSolve can be used to simulate slightly complex multiphase flows, as well as dilute and disperse flows. By combining the capabilities of EDEM, because as EDEM is a granular simulation software that can be used to simulate the effect of particle-particle collisions and particle equipment interactions. And by combining the powerful capabilities of EDEM with AcuSolve, you have additional approaches to simulate the fluid particle multiphase flows. One such approach is AcuSolve EDEM one-way coupling, where we still resolve all the particle contacts and particle equipment contacts, but we take into account the effect of fluid on the particle phase flow, but the effect of particle is not realized on the fluid. This is really suited for dilute phase flows and quick design iterations in order to concentrate more on the solid phase flow rather than the interaction between the two phases. And we have is the AcuSolve EDEM two-way coupling, which can be used to simulate the effect of two-way interaction between particles and fluid. Here, each particle is tracked individually, and the fluid particle drag forces are calculated by AcuSolve, and the effect of the particle phase on the fluid is also considered. This is a high fidelity approach for simulating fluid particle flows, and this is one of the solutions that we'll be focusing on today, as well as the Barracuda Virtual Reactor. So going over the key features of AcuSolve EDEM coupling. So when we look at various granular multiphase flows, we have fluid flows that involve fine powders that have particles at the micron scale up to millimeter scale. And then you also have flows in industries like mining, where you have particles that can be of a much larger size, and various types of industries where you have a particle size ranging in between, like the agriculture industry, where you have particles in the range of millimeter scale. And all these particles come in different shapes and size distributions as well. And using AcuSolve EDEM coupling, users can simulate any number of material types, and these can be of different shapes and sizes. Like if you want to simulate a powder, which is very fine bulk solid, you can simulate them using a spherical model. Or if you want to simulate the interaction of non-spherical particles like plate-shaped particles or discs or ellipsoids, you also can use the non-spherical particle shapes such as polyhedral or spherocylinders and multisphere particles to simulate the non-spherical particles. And in order to take into account the effect of fluid on these non-spherical particles, we support both spherical and non-spherical drag and lift models. And in some applications, it's really important to take into account the orientation of these non-spherical particles with respect to the local fluid. We also support orientation-dependent drag, lift, and torque models as well. And another feature that we have is the two-way heat transfer. So we can also simulate the heat transfer between the solid and fluid phases, and this is also supported. And in addition to the heat transfer and as well as momentum transfer, we can also simulate the drying of particles such as fruit grain drying or drying of ore particles as well. So using the mass transfer feature in AcuSolve EDEM coupling, users can simulate the process such as tablet coating and drying, as well as rotary dryers and things like that. In addition to the features that we have looked so far, one of the strongest capability of AcuSolve EDEM coupling is its capability to model complex system dynamics by using the mesh motion capabilities of AcuSolve. So AcuSolve is based on finite element method, which supports unstructured meshes and can tolerate highly skewed mesh elements while still being stable and giving accurate results. And using the strong mesh motion capabilities of AcuSolve EDEM coupling, users can simulate processes like grain separation inside a combine harvester. Like you can see in this example, we have two types of motion that are happening. There is oscillation of the sieve, as well as a blower, which blows air onto the grain that is introduced into the system. And the process of separation can be simulated here accurately by taking into account by capturing the accurate motion of these complex components. And all of these drag, lift, and torque models can be customized through user-defined functions in AcuSolve, and also using the API capabilities of EDEM, users can implement custom contact models as well as factories. So these powerful customization capabilities can be used to an effect that you can implement your own drag, lift, and torque models that you develop through experimental testing or any other research that you do at your companies, and also want to experiment with different contact models that can be implemented through the API. In addition to the contact models and customization, we also have a very powerful Python-based post-processing utility called EDEMPy that can be used for advanced data analysis, that you can extract data at the particle scale and use further data analysis and visualization that can provide valuable insights into the system even at particle scale as well as the full system level. And our coupling comes with a wide range of help manuals and documentation that can be used to train your engineers, and even from beginners to advanced level users. We have tutorials that cover the step-by-step process of setting up these models and understanding the behind it and how to set up a particular use case, as well as industrial examples and e-learning modules that can help you get the coupling and even the software implementation, everything. So using AcuSolve EDEM coupling, we can simulate a wide range of industrial bulk material flows, ranging from agriculture industry, pharmaceutical and process industries to mining and metallurgical industries as well. So here we look at some of those applications. I should let you know that there are many more applications that we can handle. This is just a subset of a very small subset of all the applications that can be solved with AcuSolve EDEM coupling. So if you look at agriculture industry, we can simulate the processes like grain separation inside a combine harvester. We can simulate sugarcane harvesters, seed spreaders, seed distribution tower, as well as lawn mowers and residue spreaders, and many more in the agriculture equipment industry. And in the process and the pharmaceutical industry, we can simulate fluidized beds, booster coated tanks, and many other applications. In addition to that, using the mass transfer capabilities, you can simulate the process of drying of materials inside rotary dryers, fluidized bed dryers, and lots of other applications. So in the next few slides, we'll talk about one such case study that was done by a customer and how they were able to use AcuSolve EDEM coupling to derive valuable insights into the process. So, yeah, Novo Nordisk is a pharmaceutical company that is based out of Europe that specializes in developing medicines for various problems like diabetes and lots of other diseases. So they were able to use AcuSolve EDEM coupling for simulating the process of powder discharge through a hopper. So here we look at a pneumatic conveying system that is replicating the actual plant. So pneumatic conveying is a commonly employed process for transportation of bulk solids in industrial manufacturing processes. However, such process involve challenges like plug flow and blockage that are present in systems and lead to higher maintenance requirements as well as reduced product quality. So these problems are particularly common for fine bulk solids like powders and cohesive materials. These problems can be sometimes traced to this feed hopper that we're looking here, where processes like arching and rat holing result in intermittent discharge and pressure surges. So developing an understanding of the complex interaction between the operating conditions that are applied and the bulk solid properties that give rise to this phenomena can lead to an improvement in process operation. However, relying only on physical experiments can be expensive and time consuming. Therefore, our customer or user looked for a numerical model that we see here. And in this work, the aim of the study was to identify a relation between the system operating parameters and the powder properties to the overall efficiency and performance. So a two-way coupled CFD modeling approach is used here. Model an axisymmetric hopper system, which is connected to a horizontal pipe. And the bulk solid is modeled with DEM particles with a adhesive contact model to model the cohesive nature of the powder. And the airflow is modeled with AcuSolve. And we performed a parametric study by varying the pressure difference that is applied across the system with the aim of relating the applied pressure drop with the system performance. The predicted evolution of the mass transfer rate. So we have three different pressure drops that are applied, and looking at how the mass transfer rate depends on the pressure drop that is applied, we can see there is more or less a linear relationship between the pressure drop that is applied and the mass transfer rate across the system. So we can see that here in this graph where we have 3 different pressure drops, and as we increase the pressure difference between the inlet and the outlet of the system, we can see the improvement in the mass transfer rate. In addition to this, there was a study that was performed to analyze the effect of extreme pressure drops. So we have seen that as increasing the pressure drop, we have better mass flow rate. But is that all? Like, what if you go to an extreme pressure drop? So we have simulated a comparison study where you're comparing 2 different pressure drop values. One of them is an extreme pressure drop of 65 kilopascal, and it's a medium cohesive material. So as we increase the pressure difference, we can see that the mass transfer rate kind of changes from a linear transfer to a nonlinear behavior, and we behavior like a propensity for arching and collapse here. So this study revealed that even though the mass transfer rate is improved, the propensity for arching and intermittent discharge also increased at higher pressure drops. So the mass flow rate is nonlinear, and also so we can see if you look at the mass transfer rate at the outlet, so there's more fluctuations and intermittent discharge at higher pressure drops. And also looking at the compressive forces on the particles. So with higher pressure drops, we see that the compressive forces increases, which can lead to agglomeration and also material buildup at the outlet. In addition to the study on operating conditions, we also looked at the material properties of the powder. So what if we have a very cohesive material, and how does the system performance depend on the cohesive nature of the material? So in this study, we fixed the pressure drop at 20 kilopascal and just simulate 2 different materials. One of them is a medium cohesive material and the other one is high cohesive. And looking at the results that we were able to get out of this, for the high cohesive material, the arch stability increases, and that leads to a highly discontinuous flow behavior. We can see that the stresses are at the pipe bend are higher, so that leads to like high consolidation, and it can result in agglomeration and clogging of the pneumatic system. So for such high pressure drops and high cohesive for a high cohesive material, we see there's a highly discontinuous flow behavior. So studies like this can provide valuable insights into the complex relationship between the operating parameters, the bulk solid properties, and various other things. And these things need to be studied carefully. And CFD numerical modeling approach can be greatly helpful for that. Like you can see from this testimonial from our customer, which is helping them improve the overall efficiency of the process. So far, we have seen from a high-level overview an introduction of the products EDEM and AcuSolve, and how these two tools can be combined together to simulate a wide range of flows, like ranging from just right granular flows, which are highly dependent on the particle-particle interactions, to fluid flows that can be simulated with AcuSolve, and also a wide range of particle-fluid loading ratios, which can be handled with EDEM and AcuSolve very comfortably. So, and we have seen this from the physics point of view, but once we add additional layers like the scale and complexity of the system, like what if you want to simulate a large fluidized bed with billions of particles, or more than 50 million, 60 million particles, or any other process that involve equipment that are of a very large scale. And if you throw in additional layers of complexity like chemical reaction between the particles and fluid, so this can make this overall process even more challenging, and achieving or running simulations in a reasonable way with less computational cost can be really challenging. But our partners at CPFD, which is Computational Particle Fluid Dynamics software, have developed an extremely powerful tool that is suited for situations exactly like this. And now I would like to invite Peter Plazer, Vice President of Operations at CPFD Software, to talk about the solution Barracuda Virtual Reactor and how this can be used as a complementary tool to simulate complex industry scale particle fluid flows.
Thank you, Ravi. And I think at this point I'll take over presenting, and it's really my privilege to be able to speak about how this all complements. So if somebody will go ahead and offer me the screen share. While we're doing that, I will remind everybody that the questions, you don't have to wait till the end to get the questions in. And it should be coming across on my screen now, I believe. So if you have some questions, please go ahead and do that as Ravi's speaking, as I'm speaking. And with that, let me launch into introducing Barracuda Virtual Reactor. So first of all, our company, CPFD Software, we are advancing multi-phase simulation and technology specifically for fluidized particle systems, such as fluidized bed reactors. Our product, Barracuda Virtual Reactor, it models the three-dimensional transient multi-phase, so that's the fluid particle hydrodynamics, how the gas particle or liquid particles are moving, affecting each other, the heat transfer, and the multi-phase chemical reaction at the large scale in industrial units. And we're super excited that for the past six plus months now, Virtual Reactor is available through the Altair Partner Alliance. So you can use your Altair units on our Barracuda Virtual Reactor as well. Virtual Reactor is it's a physics-based engineering software package. So for CFD users, there's CFD in there for the fluids. It has Lagrangian particles. We'll talk about that in more detail in a moment. Really is the only one that's commercial software focused specifically on this large scale chemically reacting fluid particle flows, so complementing Altair's other tools in the space. It is a full software package, so it comes with the user interface, the solver, post-processing, and it really is easily deployed as your company sees fit. Some prefer to run on-premise. There's a big move toward cloud adoption. It runs on both. It can run on Windows or Linux operating systems. And the parallelization is with NVIDIA GPUs, so you see excellent scale up, and we'll get to that in a moment as well. There's really two types of systems that Virtual Reactor is used to model. The largest proportion of use cases, and certainly historically the only one at some point, was gas phase domain with particles. So picture a fluidized bed, as I'm showing here. This is a small FCC regenerator. Still get an idea for scale. Because it's gas phase, the continuum is compressible flow calculation, so multiple species, compressible gases, and then no limit to any of the materials in whether the gas phase or the discrete phase. The discrete phases are particles, could also be droplets. There's no limit to the number of those particle species, droplet species, and you're getting the full particle size distribution and other discrete properties. And all this is coupled together with the thermal calculations, the heat transfer, and multi-phase chemical reactions. More recently, we've expanded capabilities just over a year ago to also include liquid phase domains. So these are vapor liquid solid systems where it's predominantly a liquid phase with particles and bubbles. This example here is an ebulated bed reactor where you have a liquid fluidized bed of catalyst particles, bubbles moving through that in vapor liquid equilibrium with the two phases, with the liquid and gas phases. There is similarly here no limit to the number of materials in the fluid or discrete phases. The fluid's incompressible in this case, being a liquid. No limit to the number of species, still the full size distribution of the particles or the bubbles, all coupled with the heat transfer and chemical reactions. So those are really the two types of systems for which it's used. And just like Ravi was showing with EDEM and AcuSolve, there's a broad range of application areas. Historically, a very large one, it still is the refining industry with the fluidized catalytic cracking units, very large units. I'll go through an example of that in a moment. Close to that, petrochemicals, polyethylene, polypropylene, catalytic dehydrogenation processes, gasification, broad uses for gasification of coal, petcoke, and more recently, biomass for renewables or waste to fuel, so municipal solid waste gasification. Materials and chemicals, this could be cement calcination, ore roasters, power generation, these are circulating fluidized beds, and the list goes on. Really the biggest growth area we're seeing today, I would say, is in this clean technology and renewable space. I don't even know how to characterize these broad applications, but these are the energy transition applications related to sustainability, renewables, decarbonization, things like hydrogen and carbon capture, plastic recycling, materials for batteries, going down that list. And so you see the commonality and research, fluidization research, other applications, there's broad, but the commonality is fluid particle interactions at large scale, often coupled with chemical reactions. And we've been honored with a good amount of recognition in just the past few years. I won't go through this list other than to say it spans from things like refining well-established industries to a lot of emerging technologies in the sustainability space. And we've been honored with that. A few things I want to say briefly on sort of what sets virtual reactor apart for these large-scale fluid particle systems. And here's a few of these things. First and foremost is the discrete particle properties. Just like for you DEM users out there, every particle size matters. It's the whole mixture, not a single size that typically captures behavior. And so with Barracuda Virtual Reactor, both on the inputs, whether it's a particle size distribution or other discrete properties, composition as we're showing here, and not just on inputs, but throughout the calculation, the evolution of things like size, composition, temperature, history, resonance time, all is on a discrete particle basis. So every particle has its own behavior. Virtual reactor also does model the full range of solid loadings. And I love this animation, animation on the left. On the right is actually a video from a cold flow experiment at National Energy Technology Laboratory many years ago. But what I love about it is you have regions that are fairly dense, still fluidized flow, more energetic and bubbling, quite energetic, fairly dilute, more pneumatic transport, some areas that are almost entirely empty of particles, and the full range of solid loadings is captured in the same simulation without knowing in advance where it'll be dense or dilute. And this is coupled with that thermal, the heat transfer, and the multi-phase reactions. In this example, we have the gas particle motion here shown on the left, and then the heat transfer. You have a hot regenerated catalyst, cooled as the vaporized droplets come in. In this case, a very simple four-lump model showing evolution of various gaseous species while depositing a coke on the catalyst. So the reactions are multi-phase, both in this case in the gas and on the particle level. And it is built for industry. So we'll get into a minute of like, well, how does this all fit together? What does EDEM AcuSolve do? What does Barracuda do? Really, the point here is this is built for that large scale with that added complexity. And so you're looking at units that could be 10 meters in diameter filled with particles that are less than 100 micron on average. And so the scale, the complexity is going into a lot of the assumptions behind it from the beginning to get that speed. And this is really where the scalable GPU and even multi-GPU acceleration comes in. We were an early adopter and actually a preferred partner of NVIDIA in their ISV partner program. And so our parallelization was on GPUs. And for those who aren't familiar, here's maybe one generation back, NVIDIA A100, these things have like 10,000 or 20,000 cores. You can put multiple GPUs in a machine, and some early benchmarking on our first multi-GPU release, and this is presented several years ago already, but showed anywhere from say 50 to 400 times faster than CPU, just running on a single box on a workstation computer with 1 to 4 GPUs. And we've seen scale ups over 1000x now. It does come with powerful post-processing and also extensible. So just like Ravi mentioned, you can make those pretty animations, but you can also dump the raw data out and process it with Python. if you want to take that further. And I will brag on our support team for a moment. It does come with full support. So I love this graphic because it shows the web meeting here, looking at not just the inputs to the software or the visualization outputs, but even what might be happening. How do you put your chemical reactions? Are they suitable for your system? The support team are people who use the software every day themselves. And so if you're licensing Barracuda Virtual Reactor using your Altair units through Altair, you still get access to our full support team. And so let me just illustrate a quick use case. This is taken from the refining industry. This is the Geelong refinery in Australia. This is a bird's eye view, high flying bird. But somewhere on this complex is something called a fluidized catalytic cracking unit. And following a change they made, this is back in 2011, this fluidized catalytic cracking unit started to see some transient temperature excursions. The flue gas line was getting hot and would run away at times. And what would happen is the operator would intervene to the point where they started pulling back throughput. It was actually costing them tens of thousands of dollars per day. And that's all documented in, and you can ask me for the reference after or make a note of this when we post the playback. There's full publication behind this with more details. I'll just give the real high level overview. So some change was made in this large industrial unit, and here's what it looks like. So here's an image from a turnaround where once every 5 years they take this down and make changes. So if you're going to make changes, you want to make sure you're doing it right and reduce that risk of any unexpected downside. So what we're looking at here, just to get an idea of when I say scale and complexity, this unit on the left is the regenerator. Over here's a reactor, this distillation column. So you're getting a feel for scale. You have one shot to open this up and make changes. The Barracuda Virtual Reactor model of the regenerator was used. And again, you're seeing on the left, the gas particle motion. Second from left is the temperature. There's some non-uniformity there. The blue-white there is the oxygen utilization. It should be burning up all the oxygen in the unit. And it should be a full burn unit, so there shouldn't be any CO leaving. But when we're looking at where's the concentration of CO still present, the green on the right shows that. And we see is this asymmetry. And I won't go into all the technical details. The paper outlines that. But needless to say, using the software, they're able to identify the root cause and then do virtual testing of various alternatives. They actually implemented this, so the simulation indicated which changes would be beneficial, implemented during a turnaround in 2016, and then had the luxury of comparing a year's worth of operational data, both before that turnaround and after. They found a few things. The average afterburn was lower, just a little bit, but significant as you're getting closer to the metallurgical temperature limitations. But the transient excursions where these temperatures would run away and the panel operator would have to intervene, this went down 75% by simple changes. And they were able to get 4% more throughput through the unit. And again, as it says in the paper, they didn't want to put an exact number, but they said it was addressing an issue that was costing them tens of thousands of dollars per day. And so just gives you a feel, as you look at the different cases, how Barracuda Virtual Reactor really complements the other Altair tools. And with that, I'm gonna transition back to Ravi, who's gonna tell us about, you have all these different tools. He's gonna start the dialogue about how you can have some options and make some selections as to when to use which and what those trade-offs are. So Ravi, go ahead.
Yep, thanks, Peter. So far we have seen various solutions that we have in the Altair software ecosystem, and now we are partnering with CPFD to bring in Barracuda Virtual Reactor that can even elevate all the capabilities that we have and go to the next level of scale and complexity that we can solve with in terms of the fluid particle multiphase flows. And so we might have a question. So we have presented various solutions. So how can I choose what solution is appropriate for my particular use case? So the next few slides, we'll try to attempt that. And it's pretty clear that it's it's not a straightforward answer. But okay, let's say you have a simulation system where the effect of fluids on the particle can be neglected. It's pretty much non-existent or negligible that you can ignore it. So definitely EDEM is a solution for that. So you can have various particle sizes and loadings where you probably don't need to consider the effect of fluid, go for EDEM. And another solution on the other end of the spectrum is you have a very dilute dispersed flow or just no particles at all. AcuSolve is a solution for that, where you don't need to consider, you don't need to have a specialized DEM solver to resolve all the particle motion, because the particle motion probably doesn't have an effect on the flow, or it's there's not many particle interactions, so you can use AcuSolve for that. And you have a broad range of simulations in between, where you want to study the local effects in at a smaller scale, from a lab scale to pilot scale, where you want to study the local effects. Definitely EDEM AcuSolve is a solution. When you go to large scale, Peter.
Yeah, and that's really where Barracuda Virtual Reactor comes in, where it's not necessarily the local effects where, you know, around a jet, a particle pushing on another particle, but really the bulk behavior of the overall large scale system. That's really where Barracuda Virtual Reactor complements that. You know, similarly, we're talking about physical scale, but you also have things like the number of particles to model. So in the type of unit I showed, that FCC regenerator, you also have very large physical particle counts, and these really can't be, you know, reasonably resolved with all that complexity with DEM. Where in contrast, Ravi.
Yep. So in medium to small scale systems where the particle counts are reasonable, that you can run a simulation in a reasonable amount of time. So we can go with AcuSolve EDEM, or go with EDEM with coarse graining, so that you should be able to solve reasonable amount of particle counts up to like 5 to 10 million for a couple systems. You can solve even higher particle count, but the amount of the return on investment is diminishing when you go with the very large particle counts. And so when you study the medium to small scale systems, the particle contacts can be resolved with EDEM. And if these interactions are critical to the solution, like if you have fluidized beds that are where the particle to particle interactions are critical, or systems like combined harvester, where you have regions where the particle bed or the particles are agglomerating at a certain location, so there's accumulation and the contact forces are critical, and you need to accurately resolve these particle contacts. Definitely EDEM AcuSolve is a solution for that. But when you have hydrodynamics as a dominant, Peter will talk about that particular case.
And exactly, and there's an overlap in all this, but you know, for Barracuda Virtual Reactor, typically is most suitable when the drag force is dominated, the fluid particle hydrodynamics. You know, there certainly could be areas that are interparticle contact dominated, but Barracuda is typically where it is the fluidization and the drag is dominant. You know, and this also goes to things like shape. And what you're going to see with all these is there is some overlap here, where the tools do certainly overlap, and you have that flexibility. But let's take shape as the example. A virtual reactor is capturing the bulk effects of the shape. You know, each particle is still discrete Lagrangian, and so drag models that take in things like sphericity or shape effects can be captured, or otherwise they're typically calibrated based on the real particles. The shape can indirectly affect things like collisional models. Surface area certainly directly affects heat transfer and reaction models if the chemical reaction is surface area dependent. But in Barracuda Virtual Reactor, shape is not directly computed. DEM is different than that.
Yeah, so when you have systems like blast furnace, where you have a completely packed system, there's little room for air to flow through that, and calculating the heat transfer between particle to particle through contacts is also really important. And systems like we just talked about combined harvester, so you have both the areas where it's much dilute, where the hydrodynamics is dominant, but also there are locations where you have a particle bed that kind of forms on the sieve and Schaefer, right? And there, computing the particle-particle interaction is really important for determining how closely the particles can be packed. So it's really critical to this whole solution. So since DEM directly computes the contacts, it resolves each and every contact, the shape is inherently included in this contact. So EDEM and AcuSolve is definitely the solution for that. And so again, like just reiterating the point. So particle-particle interaction and hydrodynamics are the primary concerns in EDEM and AcuSolve. But if particle-particle interaction can be resolved at the global scale, but not at the detail scale, then and also additional things. So
yeah, that's where virtual reactor really then will couple that with the not just the heat transfer, but the multi-phase reactions. And it's not so simple. So on this left, we're saying, okay, maybe moderate particle counts on the lower end of that axis, that's EDEM AcuSolve, and the higher end is larger scale. But there's the details matter. So take moving geometry. That's actually a very complex model, but the moving geometry often affects directly that particle motion and pushing. So with Barracuda Virtual Reactor, we do have some very limited capabilities for moving geometry, but generally we say, you know, that Barracuda Reactor is not a good fit in those cases. And Robbie, I'll just brag on you for a minute. That I don't know what you called it, a combine harvester, but that moving fan and then that moving blade. I mean, that's what you all do. That's beautiful.
Yep, exactly. So like, I can't highlight or mention the capabilities of EDEM and AcuSolve when it comes to mesh motion. It's really too good, and the type of motion that we can simulate are like any motion, like even rotation, translation, combination of both. So, and EDEM AcuSolve is really suited for those type of applications. And like I said earlier, so it's really hard to kind of put this in just a 1-2 dimensional plot here. You know, it's there can be cases that can be complex and probably doesn't actually fit into this description that we have. So we have many more cases. You can always reach out to us to if you have any questions about deciding which tool is right for your application. Just reach out to us. We can help you navigate through that. But the whole point that we would like to project here is that so whatever application that you have, we have pretty much all the solutions in that are appropriate, that can give accurate and good results for your particular application. And all those tools are available in a single license. So again, yeah, reach out to us if you have any questions. And with that, we would like to summarize this. Dave Curry will talk about.
Yeah. Thank you, Peter, and thank you, Ravi, for sharing your insights into AcuSolve, EDEM, and Barracuda. And like I said at the start, granular material fluid problems, they exist everywhere, and the complexity of applications involving particles and fluids can be significant. And EDEM, AcuSolve, and Barracuda offer engineers a way of capturing these complexities and designing effectively for such behaviors at a range of scales, all the way from the laboratory up to the largest examples we see in industry. Each of these solutions has its own strengths and means we can cover a full range of particle counts, application scales, and complexities. So we've explained some of the ways you can choose which product is right for your application. And if you have any questions about that, please do get in touch with the Altair and the CPFD software teams, and we'll be on hand to help guide you. And the last point I want to just repeat and stress is that crucially, all these solutions are available today on Altair units. So just before we go to questions, I also just want to talk a little bit about some ways you can find out more about both the solutions we spoke about today. So on the Barracuda Virtual Reactor side, there's a page on the Altair website. You can see the link there. The team at CPFD, they've got some web-based training coming up. The next class is next week. So we're running March 25th to 29th, and then another session in April. So you just need to send an email to the address on the screen there to get yourself registered. And then later on this year, There's the Barracuda Virtual Reactor Users Conference that's being held in Chicago, so that's going to be a great event, I'm sure. And yeah, I'm sure we'll be there to look forward to meeting you at that point as well. On the Altair side with AcuSolve and EDEM, again, we have virtual instructor-led training classes. We've got ones introducing EDEM, introducing the CFD solutions we have. These are available on the learn.altair.com website alongside some e-learning. And then our usual support address, if you have any questions, is shown there as well. And to reiterate, if you want to get your hands on any of these and you've got Altair units that are APA enabled, then just go to the Altair One Marketplace and you can download EDEM, AcuSolve, and Barracuda today. So thank you again to Peter and Ravi, and thank you all for attending. We've got maybe just under 10 minutes to be able to have some Q&A. So some questions have come in. Peter, Ravi, if you're able to unmute, I can share some of the questions with you and we can decide who answers from there. So
go for it.
Yeah, okay, so first question I have, I guess this was coming in, Ravi, during the EDEM AcuSolve part of the presentation. And the question was, is it possible to analyze magnetic powder? Now that might be more of an EDEM question, and so I might start with that, but maybe we can talk about it in the context of the coupling as well. You know, EDEM doesn't have a built-in magnetic material model, but we do have extensive API customization capabilities. So if you know the physics you want to implement on the particle side, then there's a very good chance that there'll be a way of introducing that sort of customization into your EDEM simulation. Ravi, anything else you want to add from the coupling perspective to that question?
No, I think, yeah, so like you said, it's most probably a particle side of thing, but if there is any question about how the fluid affects on the particle that being included with when it comes to magnetic forces, yeah, we'll be able to help you. So yeah.
Okay, good stuff. Peter, one question that came in while you were presenting, and this question is, what do you think about the possibility of using this methodology? And so I guess the question is, does Barracuda Virtual Reactor do this? Using this methodology for simulating sag or ball mills?
Yeah, so some people have done that. So as a company, we license the software, we support customers, we also have a services group. I'm not sure we've done that ourselves. I do know that some aspects of that have been done when you're looking at the fluid flow dragging particles around. Obviously, we don't have the moving parts, and so that it's been limited. But I believe I've seen some publications where people have used it. Maybe that's one that we could reach out after and discuss. We also have, I'll just put a quick plug in there. On our website, there's a resources tab and there's a resource finder. And usually the first thing I do when I try to answer these, I'm not going to do it here while sharing my screen, but I pull up the website, go to the research finder, and I start typing in a few keywords. And really there we're seeing not just what we published, but we're trying to get a good database of what's in the literature and link to if that's available on Science Direct or elsewhere. People that have published. And so we have seen a little bit, but I'm just not the expert on it, so I can't speak definitively.
Okay. Yeah, I'll just add actually that from simulating some of the material behaviors and mills, that's an area where DEM and EDEM in particular is strong. You can look at things like the breakage of particles, things like that. So if the person asking that question is still online and is interested in discussing more about sag or ball mills, as well as potentially looking at Barracuda, I would also advise taking a look at EDEM as well for that particular application. Ravi, this is a question for you. What range of particle size is the AcuSolve EDEM one-way coupling valid? So it sounds like the user's is experienced with AcuSolve EDEM. They've been looking at an agitated tank, and they're just wondering about getting the correct lift forces for sort of 2 to 3 millimeter particles. Can you give your thoughts on particle size limits for the one-way coupling?
Yeah, so there are multiple factors that can come into picture before we can get to a right answer. So first thing, more than the particle size, the particle concentration, like if you have a dense system, that's where the differentiation comes between one-way coupling and two-way coupling. So if you have some accumulation of particles at certain locations, which can influence the local fluid velocity, that's where you have to go to two-way coupling, and we can't rely on one-way coupling. So that's the main thing we have to look at. So I don't know exactly the details of the system, but that's the first thing we should go back and look. And the sizes, 2 to 3 millimeter, yeah, it depends on the equipment as well. So if it in relation to the equipment, if those are significantly large, then you have to go to two-way coupling. But if you have a 10-meter tank and you're doing 2 millimeter particles, then you can go with one-way coupling. So yeah, we can reach out to you and look at your system. We can have a call and just go to the details. But I'm pretty sure we can handle that use case well with the two-way coupling, so we can help you with that. Yeah.
Yeah, and I'd just reiterate, I think to the person who asked the question, just if you're wanting some advice on getting appropriate lift forces, etc., just get in touch with support and we can take a look at your case. A question, Peter, on Barracuda Virtual Reactor. So the question's about, okay, you're modeling the calculations that you do. Is it entirely just straight up calculations on GPU, or are there any AI tools that Virtual Reactor kind of integrates with or makes use of to assist in the calculations?
That's a timely question. There's a lot of interest these days. So the software itself is physics-based, mix of conservation, known physics and empirical models. So Barracuda itself is not an AI tool. What I have seen and what is possible is because Virtual Reactor, let me take a step sideways. You can do everything through a nice interface. So if you're new to Barracuda Virtual Reactor, you can walk through a tree, set something up, you can visually post-process, but all that behind the scenes goes to things like text files on inputs. Solver can be run in batch mode. All the output can be brought back to the native data files. Those are not locked up. You can access them. And so this opens up things like optimization, machine learning. I know there's been a group out of the University of Birmingham that did some, I'm not going to say it right and give them full credit, but it is I don't know if it's a genetic algorithm or is a real cool way where they started optimizing their output and having the tool itself go in and change inputs and to map out the space and optimize for a particular solution. So it does lend itself toward that, but Barracuda itself is not an AI tool, if that makes sense.
Yeah, thanks, Peter. And you're right, it is timely, and hey, we should explore how Barracuda Virtual Reactor could time with some of the AI tools that Altair has as well. Maybe we could do a future session on that. Listen, I'm afraid there are more questions, but we're out of time for today. What we can do is, I assume we can see who's asked the question, so we can follow up individually. Maybe we can look at potentially, a blog post following this webinar that kind of outlines some of the answers to the questions that people have asked as well, so that everyone can see the discussion. But I will conclude the webinar today. Just a reminder that it has been recorded. It's going to be posted on our resource library. And I want to thank again Peter and Ravi for taking the time to present today. I hope you found it an informative session, and it's clarified a little bit about where you might want to use which of the tools that are available under Altair. And then lastly, also thank you all for attending. It's been great to have you, and we look forward to seeing you at a future webinar. Thank you all very much.